Okay, students, then now we will see the I controller. Now you know I controller will produce a gain and one pole at origin. Okay, now we will see the effect of I controller. So if you want to understand the complete behavior of the I controller, so without I controller, now this is the plant I am taking. See, without control means only the plant. Only the plant means 1 by S into S plus 10. Type is 1. Steady state error is somewhat more. So system is stable. Okay. Now this is the damping factor zeta equal to 5. Means damping factor zeta is greater than 1. The poles which is on the negative real axis, and of course system is stable. So now what I want to say, this is without controller, right? So now we will see with I controller. Now this is which controller? Now with I controller. With I controller. With I controller, what is I controller? I controller will produce a gain of Ki and one pole at origin, right? So now with I controller, what is the open loop control system transfer function? Now with I controller, the open loop control system transfer function G of S, which is equal to Ki by S into S, S square into S plus 10. This is the forward path gain, right? Now with the presence of controller, now this is the forward path gain. So now if you observe here, now what is the type? Now type is increased. Type is 2. When type increases, you know that the steady state error is decreased. Now for a comparison, this is 100, this is definitely less than, because when type increases, steady state error is decreases. This is the steady state behavior, because the error analysis is deals with steady state. Then what about the transient state behavior? What about the actual response? So if you want to do the transient state analysis, then we want to find characteristic equation. What is the characteristic equation? Now the characteristic equation is 1 plus G of S equal to 0. Therefore, S square into S plus 10 plus Ki equal to 0. Therefore, S cube plus 10S square plus 0 into S plus Ki, which is equal to 0. This is the characteristic equation of order 3. So this is the characteristic equation of order 3. So for order 3, or here one term is missing, then you know that if any one of the term is missing in the characteristic equation, or any negative terms are there in the characteristic equation, system is unstable. Otherwise you have some shortcut method for order 3. What is internal quotient product? 10 into 0. What is external quotient product? 1 into Ki. You know that the internal quotient product is 0, external quotient product is gain. Generally gain is always positive. The internal quotient product is less than external quotient product. Now definitely the closed loop control system is unstable. Then what the integral controller? What is its performance? Now what finally the integral controller will do? The integral controller, the I controller, decrease the steady state error, but affects the stability. Stability gets affected, am I not? The integral controller decreases the steady state error, but it affects the stability. Now previously the system is stable. Without controller, there is a stable system. Now, but with I controller, now the stable system will become unstable. Okay. So the integral controller will decrease the steady state error, but it will affect the stability of the original system. Okay. That is the here is advantage and here is disadvantage. Then there is no net use of the I controller. Okay. But no sir, I am not interested on the stability sir, I am interested only on the error sir. So if anybody's interest is like this, but actually we are not at all use that type of concept practically, then you suggest the integral controller for them. Okay, now this is without controller, this is with controller, and this is the I controller's job. Okay, note down. Okay, so this is the effect of I controller. The I controller decrease the steady state error, but it affect the stability. Therefore, before you want to connect the I controller to any plant, so that plant stability you should be checked. Without affecting the stability of that plant, then you can use the I controller. But if they affect the stability of that particular plant by using the I controller, which is not at all acceptable practically. Okay. So what is the transfer function of I controller? Now the transfer function of I controller is Ki by S. Okay, and what is the practical circuit? What is the practical circuit? Okay, so how the practical circuit? Now I am already explaining the practical circuit for P controller. Now similarly, what is the practical circuit for I controller? Now this is the practical circuit for I controller. Now this is the inverter circuit I am already explaining, because to compensate that minus value, here we use this inverter circuit. Okay, this is inverter part. Because this value is -1, right? And this is controller part. So this is now I controller or a controller. So which is similar to your I controller. Now first you just find this transfer function. What happened? So here what is this transfer function? R2 by R1, right? So 1 by SC by R, which is nothing but 1 by SCR. So this is 1 by SCR. So we can write like this, which is nothing but 1 by S into 1 by RC. So this you compare with your I controller, which is nothing but Ki by S. So where what is Ki here? Therefore you can take it as Ki, which is equal to 1 by RC. Now the students, there is no doubt. So how to increase Ki or how to decrease Ki? Okay, what is the value of Ki? How it should be increased? By increasing by the system circuit elements. Okay, so this is a practical circuit of. This is the practical circuit of I controller. Okay, so this is the finally the I controller behavior. Okay, note down. So now we'll take one more plant and we will check one by one what happened. Okay, now first I will take without controller. I just take one plant. Now this is the plant 1 by S square into S plus 10. Okay, now first we will see without controller what happened. Okay, now which means that 1 by S square into S plus 10. 1 by S square into S plus 10 means, students, so now 1 by S square means this is type equal to 2, which is good. When generally type is more, So definitely the steady state error is somewhat less. Is it right or not? Because you know that. So now what about the transient state analysis? This is the characteristic equation SS square So now the characteristic equation is SS square into S plus 10 plus 1 equal to 0. S cube plus 10SS square plus 0 into S plus 1 equal to 0. Now you already know that this is the characteristic equation of order 3 and one term is missing. So what is internal quotient product? 10 into 0, which is equal to external quotient product. What is external quotient product? 1 into 1. So now the internal quotient product is 0, external quotient product is 1. The internal quotient product is less than the external quotient product, therefore the closed loop control system is unstable. So it itself, without any controller, the system is an unstable system. Okay, without any controller, the system itself is an unstable system, but which is good at error. Okay, now such a unstable system, so which we are connected to a controller, such an unstable system is now need to improve the desired characteristics. Therefore we need to take some controller's help. Now I will take the help of decontroller. Decontroller means a derivative controller. Which controller? Derivative controller. Now this is with the decontroller. Now first of all we will see what is the decontroller. Now the decontroller will produce the controlling actions. You know that any controller whose controlling actions is proportional to rate of change of error signal. Here the controlling actions are proportional to rate of change of error signals. Therefore decontroller is also called as rate controller. Understand now? Now see what is the controlling actions. Now the controlling actions is P of t is proportional to rate of change of error signal. The controlling actions is proportional to rate of change of error signals. Apply Laplace transformation. Laplace transformation of P of t is P of s proportional to Laplace transformation of derivative is s into E of s. P of t is proportional to d by dt of E of t. So if I remove this proportionality, we'll put a constant P of s which is equal to constant into s into E of s. Now this is the constant in the rate controller, in the derivative controller. Therefore this k is called as kd, which is nothing but derivative controller constant. Derivative controller constant or derivative controller gain. Derivative controller constant or derivative controller Now this is the P controller transfer function. Now this is the proportional controller. This is the derivative controller transfer function. Now the decontroller transfer function is, now the decontroller will produce 1 0 at origin. Is it right? Now the decontroller will produce 1 0 at origin. Okay. Now we will see with a decontroller. What is a decontroller? Now the decontroller will produce a gain of KD and 1 0 at origin. Then what is a open loop control system transfer function? The open loop control system transfer function G of S, which is equal to KD into S by S square into S plus 10. Now, which is nothing but KD by S into S plus 10. So now here it is type equal to 1, steady state error. Now type is decrease, steady state error is increases. Am I not? So which is greater than 10 when we compare with the previous one. This is the steady state analysis behavior. This is the steady state analysis. What about the transient state analysis? With decontroller, now with decontroller, the steady state analysis is this. But what about the transient state analysis? Means now we need to find the characteristic equation. 1 plus G of S equal to 0, S into S plus 10 plus KD, which is equal to 0, S square plus 10S plus KD, which is equal to 0. So this is the characteristic equation of order 2, AS square plus BS plus C equal to 0. If A is greater than 0, B is greater than 0, C is greater than 0. A is 1, which is greater than 0. B is 10, which is greater than 0. C is KD. Again we can make it to 0. Now if all are greater than 0, definitely the closed loop control system is stable. So what the decontroller affected? The decontroller, unstable system will become stable. The unstable system will become stable but increases the steady state error. Here it is good, but here it is affected. Okay, it improves the system stability, but it increases the error behavior. Okay, this is the effect of decontroller. Okay, now you first note down this decontroller. Now this is the decontroller. Now what is the first point? Now what is the job of the decontroller? The decontroller improves the system stability but increases the steady state error. Okay, so it affects the steady state analysis, we say, right? Now what is the second point? Now what is the decontroller transfer function? Now the decontroller transfer function is KD into S, right? The decontroller transfer function is KD into S. So the decontroller will improve the system stability, but it will affect the error. Error means a steady state analysis. Affect the Steady state analysis. Okay, note down. One more point also we'll see first. Okay. And what is a practical circuit? Very simple, right? A practical circuit will be very simple and very similar to almost all. And this is the inverter circuit. Now this is inverter, you know that, to compensate that minus. And this part is our controller. Now see here. Now this is what is this control transfer function? R by 1 by SC, which is equal to RSC. So can I write this? This is, I can write here, okay, it's not a problem. Now S into RC. But what is the transfer function? KD into S, okay. So this is KD into S. So what is KD? KD is nothing but RC. So this is, the control transfer function is KD into S, and here it is RC into S. Now this is SS, this is KD. This is the control transfer function, and this is the inverter. This is the practical circuit of D controller. This is the practical circuit of D controller. Note down. Okay. Now students, what we can understand finally. Now even we can take the P controller, I controller and D controller. Now one controller will do one good job and another controller and the same controller will give the affected another thing. Okay. If one improve the transient, another affect the steady state. If one improve the steady state and affect the transient, right? Now like that, the problem with the controllers what we are facing. So the system original behavior is improved and original behavior is to be decreased. Means error is improved and stability is affected, or stability is improved, error is affected. So that things what we are facing so far, am I not, with the individual controller. So individual controller strength is not sufficient. So can I do the combinations of the controller such that maybe I am expecting that only one complete advantage and there is no other disadvantage. Is it right or not? So we will think that in that fashion, and we will try to design a circuit. It will work or not, we will check. So anyway, we will do the same thing. Okay, the same without controller, and this is my plan, the same plan, original plan. Error is less, but system is unstable. So but only D controller is not able to fulfill the complete advantage, right? So only D controller will not able to do that job. Therefore, now I do the combination. So now I just take a proportional plus derivative controller, PD controller, proportional plus derivative controller, proportional plus derivative controller, or simply called as PD controller or P plus D controller or whatever. Okay. So what is a proportional controller? Because you know each and everything, so you can just add proportional controller will produce a gain of Kp plus derivative controller will produce a gain of Kd and 1 0 at origin. So this is a output P of S. This is input E of S. Now what is the PD controller transfer function? The PD controller transfer function is P of S by E of S, which is equal to Kd into S plus Kp. So the PD controller will produce a finite zero. The PD controller finally it will produce a finite zero in the left hand side of S plane. Now this is the PD controller. The PD controller will produce a finite zero in the left hand side of S plane. Now we will see now with PD controller what happened. Now with PD controller, now Kd into S plus Kp. Now with PD controller, so with PD controller, what is the overall open loop control system transfer function? The open loop control system transfer function G of S, which is equal to Kd into S plus Kp by S square into S plus 10. Now type is 2. We don't change the type. So I don't touch the steady state error is also. Okay. I am not affecting the steady state analysis. Okay. Error analysis which we are not disturbing. Steady state analysis which we are not disturbed. Now, what about the transient state analysis? Now the transient state analysis. What is the characteristic equation? Now if you see the characteristic equation here, 1 plus G of S equal to 0, S square into S plus 10 plus Kd into S plus Kp equal to 0. Therefore, S cube plus 10S square plus Kd into S plus Kp equal to 0. So this is characteristic equation of order 3. What is the internal quotient product? 10 into Kd. What is the external quotient product? 1 into Kp. This is the internal quotient product and that is the external quotient product. Now this internal quotient product, if it is greater than the external quotient product, then definitely the closed loop control system is to be stable. Okay, note on this. Okay, now this should be the PD controller. We will see. So what is a PD controller finally? A PD controller improves the system stability without affecting error. And what is the transfer function of PD controller? The transfer function of PD controller is KD into S plus KP. KD into S plus KP. And we will see the practical circuit of this PD controller also. And you know that this is generally the inverter part. Okay. Now this portion is nothing but inverter, and this portion is nothing but controller. Okay. Now you simplify this circuit and compare it with the original transfer function. Okay. Then what should be the transfer function you are getting here? Now this is nothing but R2 by R1 by 1 plus SC1 R1. This is. So this is nothing but R2 into 1 plus SC1 R1 by R1. So again, if you further simplify, R2 by R1 plus R1 cancel, R2 C1 into ES. So what is the transfer function? You already know that. KP plus KD into ES. So KP is R2 by R1, KD is R2 into C1. Okay, no doubt.